Welcome to an AP Chemistry session with Ms. Taylor. We are looking at a released free response test question. And before you even begin to read the text of the problem, you should look at the diagram. And the first thing that should jump out at you about this diagram is this thing right here. Power supply. That means this is an electrolytic cell. In other words, this reaction will not happen unless you supply the electricity, as opposed to galvanic or voltaic cells who happen spontaneously and produce electricity. So let's read the description and see what else we can get out of this. Okay. Even if you had not noticed that, an external direct current power supply is connected above to two platinum electrodes. It doesn't matter what type the electrode is, but external power supply is another key phrase that they use on AP exams to tell you that this is an electrolytic cell. Okay, so in a beaker containing 1 molar copper 2 sulfate, so I'm going to write this out to the side. And at 25 degrees Celsius, so it's at standard conditions. As the cell operates, copper metal is deposited onto one electrode. They actually gave that to us. And oxygen is produced at the other electrode. Aha! Those bubbles are oxygen. And then they give us the two reduction half reactions for what happens below. Okay? So the first thing they want us to do is to indicate the direction of electron flow. Well, before we can do that, we're going to have to figure out which one of these is the anode and which one of these is the cathode. So let's go back to our half reactions. Okay? So we've got copper being reduced because it's gaining 2 electrons. And then they've got this reaction that says oxygen going to water. Okay? Keep in mind what we have in the beaker. We've got copper 2 ions, we've got sulfate ions, and we've got water. So these things are the possible reactants. So when you're looking at the half reactions, you can tell which ones need to be flipped by simply putting it into context. Oxygen is not a reactant, it's a product. So what really happens is the reverse of this. So our equation is actually 2 water going to O2, 4 hydrogen ions, and 4 electrons. And that is an oxidation process. That also means that our oxidation potential, EOX, is going to be a negative 1.23. Okay, well now that we have determined that, that's going to help us label our electrodes. Because this is oxidation, and this is our reduction. So I can label this over here. And one of the mnemonics you can use to remember which electrode does what is red cat, anox. Because reduction happens at the cathode, and oxidation happens at the anode. Now, this is a whole lot of work to get to what we're finally answering in the question. What is the direction of electron flow in the wire? Okay? Electrons always go away from the anode. So the electron flow is going to follow the wire that way. Away from the anode and to the cathode. You can think of it as running away from the ox and towards the cat, because the cat's a whole lot safer. Now we can move on to the second question, part B. Write a balanced net equation for the electrolysis reaction that occurs in the cell. Here's another thing where they're telling you what type of cell this is. So a good idea when you approach your free response questions, before you start doing the stuff, look at the diagrams they give you and read through it before you just dive into answering the questions, because they may give you a clue that will help you answer the first part. Anyway, so let's scroll down just a little bit more. Okay, since I've already flipped our oxidation half to reflect that it's actually oxidation and losing electrons, we can compare those. Remember that the electrons have got to cancel. In our oxidation half, we've got 4 electrons. In our reduction half, we've only got 2. So we're going to have to multiply this reaction by 2. And then sum them. So I'm going to write this down here. 2H2O. Going to oxygen gas. 4 hydrogen ions. 4 electrons, which will cancel. Alright, now make sure we multiply these by 2. So that's 2 of the copper 2 ions plus 4 electrons goes to 2 copper solid atoms. So we can see our electrons cancel. And when we sum this, we've got 2 water molecules, 2 copper 2 ions, and then that's going to give us a molecule of oxygen, 4 aqueous hydrogen ions, and 2 atoms of solid neutral copper. Alright, so moving on to part C, they want you to predict the sign of delta G. In other words, is it going to be positive or negative? And then justify your prediction. Well, if you look in D, they tell you to calculate it. So technically you could calculate it and then work your way backwards. But you should know that delta G for this one should be positive. And the reason why is because this is a non-thermodynamically favored reaction. In other words, it's not spontaneous. And your justification for this should be the reaction requires an external power source to happen. So the reaction requires an external power source to happen. Or to occur. Okay. Alright, but then in D, they want us to calculate delta G. Okay, so the way we do this, and I'm going to write this equation, this is an equation that is included in the formula sheet that you will receive. And the formula sheet does go on to tell you that this is Gibbs free energy, that that's moles, that is Faraday's constant, and that is cell potential. Okay, specifically to this one, this is moles of electrons. Now, you're looking at these things going, well, Faraday's constant's on your sheet. Before we can solve for delta G, we're going to have to solve for the cell potential for this. Okay, and cell potential is one of those equations that they do not give you on the exam. And depending on who taught this, you may see this a couple of different ways. This is my preferred way of remembering the equation, is that it's the reduction potential plus the oxidation potential, because you can't have reduction without oxidation. So now we can go back and scroll up and see what our values were. So for the reduction half, it was a positive 0.34. For the oxidation half, it was a negative 1.23. So that's going to give us a negative 0.89 volts. Now that we have that value, we can plug into the delta G equation. Where do we get N? N is the number of moles of electrons. I'm going to scroll up just a little bit. If we look at our two half reactions when we were solving for part B, we had 4 moles of electrons on each side of the equation. So our N for this one is going to be 4. And then F is Faraday's constant, which is listed on the equation sheet, 96,485. And that's coulombs per mole of electrons. And then our cell potential we just calculated, negative 0.89. Punching that into your calculator and then rounding it to 2 significant figures, it's going to give you 340,000 joules per mole of reaction. Now, on the AP Chemistry exam, they do allow you to just leave it in joules or kilojoules. Sometimes they'll say kilojoules or joules per mole of reaction. Either way is acceptable. They're not going to deduct points if you just leave it in joules or kilojoules. And if you wanted to express it in kilojoules, you would just divide by 1,000. It would be 340 kilojoules per mole of reaction. And we thought we were done, but nope, there's still more. But I do want to point out before we move on to part E is that our prediction matches our calculation. Remember that positive delta G values indicate a non-spontaneous or non-thermodynamically favored process. It does not happen on its own. That's why this is an electrolytic cell that we're having to supply an external source of energy to make it happen. So, continuing on the thread of this external source of energy, they now tell us that the current is 150 amps and it runs for 40 minutes. And they want us to take that bit of information and calculate what mass of copper is deposited on that electrode. So, there's a few things here that you're going to have in your back pocket in order to understand how to calculate this. For one thing, you're going to have to know that amps or amperes is the same thing as a coulomb per second. And that you can use that as a conversion factor as a stoichiometry problem. And then we're also going to use Faraday's constant as a factor. Okay, so I'm going to start from the time. And I'm going to convert that to seconds because this is in coulombs per second. Then I'm going to use this, and I'm going to put the 1 second on bottom and 1.50 coulombs on top. So up to this point, we've gotten rid of time units. We now have charge. Okay, so the other thing we have that has charge in it is Faraday's constant. So now I'm going to put the number part on bottom, 96,485 coulombs, and the 1 mole of electrons on top. And now you may be wondering, how do I get from electrons to grams of copper? Well, the copper that we had was copper 2. And so for every 1 mole of copper, there's 2 moles of electrons. So I'm going to put 2 moles of electrons on bottom, 1 mole of copper on top. And we are almost there. At this point, hopefully you know that we can use molar mass to convert from moles of copper to grams of copper. And punching that into your calculator and rounding your answer to 3 significant figures, you should get 1.19 grams of copper have been deposited on that electrode. And the last part to our question, because on the AP Chemistry exam, they like to bring in multiple concepts into one free response question whenever possible. Now they're pulling in some gas laws because they want us to calculate the dry volume in liters, measured at 25 degrees Celsius and 1.16 atmospheres of pressure, of the O2 that is produced. So this is not STP. So that means we're going to have to use the ideal gas law. Which is PV equals nRT. So pressure, volume, moles. R is the gas constant, and you will have to choose the correct one from the list on your formula sheet. And then temperature in Kelvin. So we are looking for volume. They gave us the pressure. They gave us the temperature. I just told you that R you choose from a list. So before we can find volume, we're going to have to find the number of moles, which is just traditional stoichiometry. But you're picking up from your answer to the previous question. So if we have 1.19 grams of copper produced, how many moles of oxygen are produced? Now there's molar mass, and to complete the calculation we're going to need the correct mole ratio. So I'm going to scroll back up so that we can see our balanced chemical equation, showing us that there's 2 moles of copper for every 1 mole of oxygen gas. So 2 moles of copper on the bottom, 1 mole of O2 on the top. Alright, so in our calculator, I'm not going to round this very much, because if you round too much in your intermediate calculations, that can affect your answer in the long term. Also, if you've got a graphing calculator, you're just going to be able to plug this in anyway. So now that we've got the moles, we can plug into the ideal gas law. So our pressure was 1.16 atmospheres. We're looking for volume. We've got our number of moles there. Next is R. Now, the way that you choose R is by matching up the unit used for pressure. So if you look at the list, there are several different numbers, and they're all in liter something per mole Kelvin. So the one that has liter atmosphere per mole Kelvin is the one we need, and that value of R is 0.0821. And then we have to take our 25 degrees and convert that to Kelvin, which is 298 K. So multiply these, divide by 1.16. All of our units will cancel out. And on this problem, I'm going to round the answer to 2 sig figs because of the 25 degrees Celsius. And so in your calculator, you should have gotten 0.197 something, which when you round that up, will make it round to 0.20 liters of oxygen gas. And that completes the problem. Thanks for watching.